Thanks, Adam. Hi, good morning. ReactNext. Good morning. All right, so shalom, shalom. You know, this still feels like home. Now, why did I say that? Well, instead of the who am I slide, maybe I can just do a who am I story. Now, perhaps like many of you, I learned to write my first lines of code right here in Tel Aviv. Now, this was back at the turn of the century, and I was hired by a startup called Hypernix, and I was actually not hired to do coding. I was hired to do tech support by chat all night long. And, you know, forgive me, I had to run over yesterday and take a photo of the where the Hypernix offices used to be, and I realized that this may not look like much today, but I can assure you back then it looked, well, pretty much the same. So going back to Hypernix, their product was a chat app called GUI, and GUI had a cool feature where when you would type, the letters or characters you would type would kind of float up onto the screen and sort of ease into place, and your friends could read them. And I remember being so envious of the developers that were building that. Of course, I never met any of them because they all worked during the daytime. But I just felt like I had to learn how can I make stuff move on the screen. So I did what people did, which is I bought a book in English, and I had a friend bring it like 4 weeks later. And since I was already up all night, every night, I just kept on working on this and learning how to animate things on a timeline and with code. So first, I drew a ball, and then I made it move, and then I did a whole lot more of that. And I found myself suddenly in a whole new world of joy and creativity. And back then, companies would pay you to do this stuff, this fun stuff. You know, they would hire people for titles like Flash Master. They called us names like Flashiste, which sounds like a slur, but it's really not. And I can assure you that, you know, these were some of the most exciting, lonely nights I'd ever had in my entire life. If any of you can remember that moment when you first felt the spark of joy, you know, with your work, or when you realized that the love of building cool stuff was firmly in your DNA, I really hope you'll just come up and introduce yourself and tell me a little bit about it during one of the breaks today. So, my name is Kevin Maes, and just like the many iterations of ECMAScript over the years, my career has also evolved. And for the last couple of years, I've been working with a great team at Stately, building visual diagramming tools for developers and teams just like yours, based on an open source state machine library called XState. So now you're all caught up, and I still live on the Mediterranean coast, but this time on the other side in Malaga, Spain. And every day I wake up to the sights and sounds of flocking birds. It's actually very nice. And it reminded me of some of the animations back in the day. Also, it got me kind of curious about some of the algorithms that were inspired by nature. And that's how I came upon genetic algorithms, also known as GAs from now on. So these are not new. They're actually part of a broader area of computing called evolutionary computation, which itself is part of artificial intelligence. So please join me as we go back in time to see the birth of genetic algorithms. All right, so we begin in an era where computer scientists all had black and white headshots. Meet Lawrence Fogel. Now, Mr. Fogel in the 1960s had an idea called genetic programming, and he wanted to simulate the process of evolution using state machines. Now, Fogel's approach involves creating a whole population, that's an important word, of finite state machines, and what he would do is he would see whether they could adapt and optimize their behaviors over successive generations through selection and mutation. We'll look into all that. Now, he used these principles to predict time series data, things like stock prices or weather, based on past values. Okay, shortly after, a professor from the University of Michigan named John Holland built on top of these ideas to create genetic algorithms. And these two disciplines, they are joined by a couple more, and they all make up the most popular algorithms of evolutionary computation, but by far, the genetic algorithms are the most popular. I want to go back to the father of genetic algorithms, John Holland, So he got a physics degree from MIT. This is pretty impressive. He got a mathematics master at the University of Michigan. He was actually the very first person to get a doctorate in computer science at the University of Michigan. And then he went on to teach as a professor in 3 departments there. 1, computer science, of course. 2, electrical engineering. Okay, why not? And 3, you probably guessed it, psychology. So I think it's safe to say that Mr. Holland was a highly evolved human being. Now, Holland's breakthrough came when he wanted to look beyond machines to look to nature itself. He was inspired by Charles Darwin's theory of evolution by natural selection. Now, his work tested whether the principles of biological evolution, like selection and crossover and mutation, could actually be applied to artificial systems in a way to make them more adaptive and even intelligent. So in 1975, he wrote his groundbreaking work, which basically detailed the theory and the practice of GAs, and he combined biology, computer science, and math, all to basically solve optimization problems. So why do we need all this? Well, the main purpose of a GA is either to arrive at a desired behavior, or an optimal design, or to solve complex search problems. So imagine if you have a problem, and you're given an infinite amount of times to try to solve that problem in a random way. You can guess that perhaps someday you'll probably figure out that problem, but it's just going to take a very long time. So GAs use the concept of natural selection and survival of the fittest as a way to basically super speed up that process. Now, what kind of problems can we solve here? Well, GAs can be used to design efficient network topologies. So perhaps you've heard of something called the traveling salesperson problem. Companies like UPS have basically used GAs to optimize their delivery routes, making them more effective, cost-efficient. Also, there's automated testing, things like model-based testing, where you can actually generate many test cases but then narrow them down using GAs so that they're more efficient. Game strategies is another one. Games like chess and Go can be used to enhance AI in those games. And educational institutions have also used this to basically optimize timetables to be conflict-free. Now, even complex hardware design can use a GA. For example, in 2006, NASA launched the Space Technology 5 mission, or ST5, and its goal was to test in space innovative technologies. So they launched 3 satellites, and each of these were equipped with all these new technologies, things like low-power batteries and propulsion systems, thermal regulation, and also communication devices like antennas. Now, designing antennas by hand was very time-consuming and labor-intensive. So ST5 included what is known as an evolved antenna, and that's basically an antenna that was created by a GA on a supercomputer. It all started with simple antenna shapes, adding or modifying them in a sort of semi-random manner. Now, these were evaluated based on their fulfillment of design requirements and each given a numerical score. So NASA is building this big space satellite. Obviously, it's much easier to iterate thousands of times on a design using a computer before finally committing all of the resources to build and manufacture, assemble the full-scale antenna. So what did the finished product look like? It looks like they got a bent paperclip. But this tiny, weird-looking communication antenna featured low power consumption and faster build time. NASA still uses evolved antennas today for their future missions. And the reason is because mission requirements change frequently. And evolved antennas are cheaper and better at adapting to changes like that, all thanks to GAs. OK, so how does this work? There are several steps involved in a GA. The first one is the population initialization. Now, that only happens upfront once. Then we have evaluation, selection, crossover, and mutation. And those last 4 are going to happen repeatedly, maybe hundreds or even thousands of times. Now, each of those iterations is considered a generation, and each generation has its own new population. The GA is going to manage this sizable population of individuals, and individuals can contain their own solutions to the problem. Now, every solution to the problem is kind of encoded in the individual's DNA. Now, you can think of that sort of as a representation or maybe a serialization of the individual's characteristics or its solution. But it's important to note that population initialization is where we first establish some variation across that population. Now, evaluation is maybe the longest stage. Here we're going to let individuals of the population attempt to solve the problem. And this could involve interacting with an environment. The most important part of this stage is the fitness evaluation. Using a fitness function, we can reward, score, or even punish individuals. And every individual will be assigned a fitness score. Now, only selected individuals get to be parents of the next generation. And this gets pretty interesting because there are many different ways to select parents based on fitness. One of the most common is the roulette wheel selection. Now, in this method, the likelihood of being selected is directly proportionate to the individual's fitness. If we add up all the fitness scores, we get sort of a whole pie or a roulette wheel. And then, obviously the higher scores get a larger slice of the pie. If we randomly select a number, then it'll land somewhere on the wheel with a greater chance of landing on a high score. But it still has a chance of landing on a low performer, which adds to the variation, and that's still very important. Now, how many parents do we need? Well, it depends, but roughly between 30 and 50% of the next generation. So for a population of 100, we might select 30 or 50 people to be parents, or individuals to be parents. Crossover involves mating parents. One thing we know for sure is that we do need to maintain the same population size from generation to generation. Now, we can combine DNA, but that does depend a little bit on the nature of the DNA. So, for example, DNA is made up of chromosomes or individual values. If those values are simply numerical, then we could perhaps just average them. But if they're not numerical, we might need to do something where we take a value from one parent or we take it from the other parent. In mutation, we have a chance to maintain variation here. One reason we need to do this is to avoid reaching something called local optima. Now, local optima is a case where the population converges on what it appears to be the best solution, but only in the immediate area. And it doesn't really have an idea about the global optimum, which is the overall solution. Now, mutation does allow for occasional variations of specific chromosomes of DNA according to a mutation rate. And of course, each of those can vary according to a mutation amount. All right, now that we've created the next generation, we return to the evaluation step, and a whole new population tries to handle the problem. Now, I mentioned that GAs can solve complex optimization problems, but I'm a kind of a simple guy, so I don't really have any complex problems. So I thought it would be more fun to try this out using some creative coding with Canvas. So let's see some examples. Okay. Okay, can everybody see this? All right, great. So, okay. We are combining the principles of genetic algorithms with creative coding, specifically with Canvas. And the goal here is we have this red circle in the middle here. And what we want to do is we want to take a bunch of randomized placed circles in different sizes and have them match that one circle. You can also see that there's some information down below where it tells us about the generation and the average fitness and things like whether we found a match at all or the current matches for the current population. So let's start over here. This is very simple. We talked about keeping things simple. There's a Canvas tag on the HTML page. All you need to do is give it an ID. You can set a width and height. Style is completely optional. And then over here in JavaScript, we have the initialization stage. Now, I just want to talk about some of the dependencies. There really aren't many dependencies in this little mini project here. There's no frameworks. There is TypeScript. There's the other thing is that this does use XState. I'm not really going to go into how to use XState right now, but the reason that I like to use it is sometimes it can be helpful to work with certain kind of algorithms and thinking of them as a state machine. Because one reason is that they give you a clear separation of the different states that your algorithm can be in and the events that it would take to transition between them. It also lets you kind of separate handling the implementation of effects or side effects. In this case, that really means writing to the canvas, drawing on the canvas, or updating some information. State machines, they can also be visualized, and that's pretty cool too. And they can also help you to pause and resume execution of an algorithm midway. So back to here, let's see. OK. So in the initialization, you can see that the first thing we're doing here is we're grabbing a reference to the canvas by its ID. And then we are getting and setting here on this line, getting and setting the canvas context. In this case, it's 2D. The other option is WebGL, which is for 3D. And then we need to go through and iterate up to a population size, basically every random circle that we want to create. And all that does is just goes and gets you a circle with an x and a y coordinate and a radius or size that's randomized. OK. Now, the next thing is the draw function, and that's obviously really important. So every time we want to draw this, and I'll just keep on kicking this off again, every time we want to draw this, we want to clear the stage with the clear rect. And then for every individual in the population, we want to draw the circle. You can look into all the different methods on the canvas context of how to do that. But the point is that we're going to draw them every single time. And then finally, here, we actually have the target circle that we're putting, which is the red one. OK. So let's say, right now, I'm going to bump this up. You can definitely do things like 60 frames per second. That's no problem for Canvas. But I've actually found that you can even go higher. So we can even put this up to like 200 frames per second, which is pretty fast. I don't think you're going to get any more gains by going faster than that. So let's just walk through some of these steps here. So we talked about evaluation. And we're basically looping over the population here. And we're going to calculate a fitness score for each one of those. So if we go into that, you can see that we're basically just, here, I'm just going to start this over again. We're basically calculating the difference of the distance and also the size difference. And then we're kind of normalizing that so that if it has a score of 1, then it means it's a perfect match. If it has 0, it's no match at all. And another cool thing that you can see here is that you can actually add some concept of weights when you're working with a fitness function. So for example, if I made any of these 0, then you can see that the size is matching, but the position is not matching at all. In fact, sometimes it's even more, different. And so that's something that you can actually really play with here. But of course, you can also make these, 1 and like, 100 or something like that. And oops. So you can do all that kind of thing. And if you see here, let's see if it's actually going to match here. Hold on. OK. I think this is going to match. So then let's just keep going. So if we look at the, down here. OK, selection. This is where we actually need to select the parents. And you can see that we have this roulette wheel selection. And we did find a match eventually at about 2,700 generations. Roulette wheel selection, you see we're basically adding up all the fitness scores to make that whole pie. And then we're randomly choosing a number. And then we're just looping through the population so that when it bottoms out, it eventually lands on one individual. And then that's the one that we're selecting at that time. And we do that over and over up until a third of the population, 30 to 50% we said. Crossover, that's very simple here. Basically, we're just randomly selecting one of the parents and then another parent. And then we're just sort of merging the child is basically taking the average of the different parent values. And then in mutation, that's, hold on one second. Yeah, here we go. Mutation, we're basically mapping over the next generation, and then we're calling a mutate function. Now, that doesn't necessarily mutate everybody, because it has passed in a mutation rate. And so we're going to spread in the original individual, and then we're going to try to see whether or not we actually get within that mutation rate. But anyway, so the point of this exercise is to show you that, basically you can take what was random circles of different sizes and positions, and you can run it through a genetic algorithm, and you can actually have the problem solved. Sometimes it takes a few hundred generations, sometimes it takes even more. OK, so the next example here that I have, OK, make it bigger. So this one basically uses several hundred particles. And these particles are going to have a very simple goal. We're going to start them out on the left side of the canvas, and we want them to basically go off to the right side of the canvas. Right? So it's kind of a modest goal, I know. But let me just kick it off and show you what that looks like. So at first, we see a dump of all these particles running in all kinds of random directions. So the motion is random, the speeds are random. You can see that none of them can actually stay on the canvas at all. Another thing you'll start to see is that they do have sort of these little arcs around them, and that's sort of a very rudimentary kind of a radar system that they have to try to detect the approaching of the boundaries. It's not very strong. It doesn't seem to be working quite yet for them. And we just sort of project a couple of rays out in front of us at a certain angle and then connect them with an arc. We also have some colors, but that's really more because as the lifespan of an individual basically approaches that of the average of its two parents, then it turns from white to yellow, and then if it starts to exceed the lifespan of the parents, it turns to orange. But you will start seeing, now we're at generation 4, that there is some sort of forward movement. And I want to talk about the fitness function, right? So the fitness function, we want to reward individuals for making it all the way to the far right, so we do that. We also want to reward the ability to propel against the walls. So we can let those individuals keep track of how many times did they successfully do that before they finally died. So they get a reward for that too. And once they do die, and many of them are still dying, then we can at least see how far did they get from the left to the right. And you'll start to see that everything is starting to move in the right direction because the environment is also broken up into several zones. So these individuals are starting to have an idea of, oh, I've already been to this zone. It's kind of like finding your car in the parking lot. You know you've been to that one and it's not there. So you actually can then remember where you've been and try to move towards zones that you have not yet visited. So we're just going to keep on doing this here. OK, so now we're up to 87%. And we seem to be climbing. That went down a bit. Uh-oh. This might be one of those ones where it doesn't do it. Here we go. Oh, we are climbing still. Do you think we're going to do it? Oh my God, 99.4? Uh-oh. OK. Well, I'm going to tell you something. Every now and then, because of the mutation rate, and because this is not an exact science, then sometimes it doesn't actually complete. And I wanted to do this live and not in a recorded thing, but maybe I should have done the recorded thing. Anyway, so I think eventually this might work, or it might not. But let's just say that we've gotten it up to 99.4%, which is good enough. Right? We're going for good enough, not perfect. And eventually, they are actually kind of moving all together. All right. So let me go back here. OK. Oops. Oh my gosh. How do I get there? I cannot grab this thing. Why can I grab this thing? God. No. Oh my God. What the hell? Oh. There we go. OK, I got it. I got a handle. All right, thank you. All right. OK, well, the demo didn't get applause because it didn't work, but at least the screen sharing is doing better. OK, so here we are. So 6 minutes left. All right. OK. I guess I kind of showed you the canvas is easy as 1, 2, 3, right? You just put on the tag in the HTML. You get an element by ID, and then you set the context to 2D. You can definitely check out the Canvas docs for the API, how to draw shapes, how to use text and do all that kind of stuff with colors. OK, some tips here. You want to always clear the canvas properly so that you don't have any artifacts that remain from the previous draw. And it's really amazing. If you use request animation frame, I highly recommend that when you're doing your own loops, because it lets the browser maximize the refresh rate. And it can be pretty impressive how fast things are moving in Canvas. One other thing is kind of like for particle systems, I mean, I generally like more like functional, JavaScript-y kind of things. But with particle systems, I actually find myself going back and kind of using more of the classes and OOP. And the reason there is just because all of those instances can kind of encapsulate their own state in terms of their size and their position and their animation parameters. You can even create a class for the population itself, for example, so that it manages all of the, let's say, the population-related things like assign fitness or select parents. Okay. Now, if you want to get up and running quickly with creative coding, I do recommend checking out P5. I don't know if you've heard of that, but it's a nice way to get started with any creative coding project. And there are some benefits there. You can read those. But basically, it's a JavaScript wrapper library around Canvas. And it's inspired by a Java-like language called processing, which is used heavily in things like generative art. And it makes things kicking it off much faster, and you can use the playground that they have there. OK. So although my use cases have been mostly these fun experiments, I feel like I've learned a lot about GAs. So for example, population size really does matter. If the population is too small, you're not going to have that diversity that you need. And you're not going to get the variety. But if it's too large, you might be doing a lot of extra work, or it might just take a very long time to solve your problem. You have to experiment with fitness. Like I said, you could tweak things with the weights. And you can really try to match your requirements in the fitness phase. In terms of selection, there are a few other methods for selecting parents. Names would be like tournament selection, truncation, or rank-based selection. And all of these are designed to basically help tweak what's known as selection pressure, which is the intensity in which the higher-performing individuals are chosen over the lower ones. And then in mutation, after the fitness, you really want to tweak the mutation, because that's where you can have a demo go well or not. And the key is to avoid this premature convergence. And on a per chromosome basis, you can also tweak the amounts and the rates. All right. OK. So, as you sort of seek to tackle some of the bigger problems that you may have in your day-to-day work, there might be ways that GAs could help you. I mean, some of these things are actually being put into practice now, and others might just be some ideas ahead that you can think about. But I think knowing how GAs work is kind of an interesting way to give you clues about how to better iterate on some of the products and projects you have. Now, there's tons of academic papers. Some of them are cool. And there's lots of videos on YouTube. But I do want to call out something called the Coding Train, if you're not familiar with this already. It's by Daniel Schiffman, and he actually has like a 5 or 6 video series specifically about genetic algorithms, where he goes into depth, and also videos about every other creative coding topic under the sun. Another thing is that I'm excited about this book, this new version of the book that came out maybe 12 years ago, originally for the processing language. But this one is A Nature of Code, also by Schiffman, and it basically has everything to do with simulating natural behavior and natural systems. And it's coming out in September, but it's going to be for JavaScript. And I admit, I do still buy books because I like that you can take them to the beach and read them there. All right, so exactly 10 years ago, this movie, Edge of Tomorrow, came out. That's the sort of like action-packed Groundhog Day with Tom Cruise and Emily Blunt. Now, I don't know if you know, but the tagline of this movie, and in some cases the title, was actually Live, Die, Repeat. And I think that kind of reminds me of a little bit of what we've been seeing with the genetic algorithms today. Now, in that movie, the hero, Tom Cruise, is basically killed off repeatedly. And every time he's fighting in this like battle zone against deadly aliens, fight for survival. And every time he dies, though, he starts all over again. However, he retains the memory of the previous lives, and he's able to use his successes and failures from the past to basically become a more evolved fighter and to succeed. And we humans, as a population, we continue to pass down knowledge from generation, from one generation to another generation and to the next generation. And we can see that these ideas of genetic algorithms have already been passed down to us through multiple generations. By the way, this is supposedly the title of a sequel that's going to come out, maybe. But until then, I really hope that you'll have some fun with genetic algorithms and creative coding. And please remember that, as long as we keep coming together like this to share our knowledge and our experience and our passions, then together we as a population can achieve any goal. Thank you very much.